Okay, Dr. Gardner here. I just wanted to talk about one of the homework problems that we had for Chapter 4, as I noticed that it was a problem that quite a few of us had some questions on. So let's go ahead and work through this, and I wanted to do this in a video format so we can kind of see how I thought through working through this problem. So here what we're told is that a mixture was prepared by adding 20.4 milliliters of a specific concentration, 0.181 molarity sodium phosphate, to 31.9 milliliters of 0.143 molarity calcium nitrate. And we have two goals here: to identify the mass of the solid that's formed in this reaction, as well as the concentration of all the ions. So we have sodium, calcium nitrate, and phosphate ions that we could possibly have in solution once the reaction is done. So let's go ahead and start by working through this. And if we have a process where we're mixing two solutions that are both ionic compounds, we would look at, well, what possible double replacement reaction would occur. So here we would have sodium phosphate. If we go ahead and look and see, sodium phosphate would be aqueous. Sodium group 1A is always aqueous, reacting with calcium nitrate. Calcium nitrate is also soluble in aqueous because nitrate ions are always soluble no matter what they are partnered up with. And we're going to undergo a double replacement reaction here, where we're going to get sodium nitrate and calcium phosphate. And so we're asked to figure out the mass of a solid, so hopefully one of these we would identify as being insoluble. While sodium and nitrate, both of those ions are always soluble no matter what they're partnered up with. And then calcium phosphate, well, our phosphate ion is always insoluble except for group 1A and ammonium. So if we look there, we see, well, it's not with either one of those, so we're going to go ahead and classify that as our insoluble compound that will be our precipitate. So now we want to go ahead and then finish up by balancing off our reaction here. And so now we have our overall balanced reaction. Now once we've done this, we're going to predict what mass of our calcium phosphate we're going to get. That's our solid precipitate that's formed here. In order for us to do this, we're going to have to identify a limiting reactant. Now why would we say that? Well, we would say that because we have 20.4 milliliters. So our volume would be 0.0204. I'm going to go ahead and convert all of our volumes to liters because we're going to use molarity. And the concentration would be 0.181 molarity for our first solution. Our second solution, we have a volume of 0.0319, 31.9 milliliters, which would be 0.0319 liters, and a molarity of 0.143 molarity. Now, if we have a volume and molarity of both of these solutions, if we go back to molarity and how we can use that, well, molarity is defined as moles of solute per liter of solution. So if I have molarity and volume, I can find the number of moles by multiplying our molarity times our volume in liters to give us our number of moles. So we can go ahead and do that for both of these, and we would find that we would have 0.00369 moles of sodium phosphate, and then we would have 0.00456 moles of our calcium nitrate. So we have the amounts of two reactants. One of these is going to limit how much of a product we get, and the other one we will have an excess. So kind of the simplest way to do that is to say, well, if I have this amount of sodium phosphate, how much calcium phosphate am I going to form? If I have this amount of calcium nitrate, how much calcium phosphate could I possibly form? And one of those is going to be a smaller amount, which would be our limiting reactant. So let's go ahead and do that. So we have 0.00369 moles of sodium phosphate. Go ahead and use our mole ratio. 1 mole of calcium phosphate to 2 moles of sodium phosphate. That's just going ahead, and we're using our mole ratio from our balanced equation. And then we can go ahead and use the molar mass of calcium phosphate, which is 310.2 grams of calcium phosphate for every mole of calcium phosphate. and that's going to give us a mass from our sodium phosphate of 0.572 grams of calcium phosphate that we would form if it all completely reacted. Now, if we would do the same thing using our 0.00456 moles of calcium nitrate. Not going to go through the explanation of how we would get there, but again, we would use our mole ratio and our molar mass, and we would see that that would lead to us forming 0.472 grams of calcium phosphate from our calcium nitrate. And so now we see, well, our calcium nitrate is going to be our limiting reactant. We see that this is the smaller value, which tells us we're going to run out of calcium nitrate before we get rid of all of our sodium phosphate. And so that tells us that our calcium nitrates are limiting reactant and our sodium phosphate is our excess reactant. So now we've done that first part that we were asked to do, is identify the mass of a solid. Now what we noticed is that we had to identify our limiting reactant because we were given the amounts of two of these, right? We were given the ability to identify the moles of sodium phosphate and the moles of calcium nitrate. Well, if we have the amounts of two different reactants, whether they would be from a mass or whether they be from molarity and volume if we're dealing with aqueous reactions, we've got to go ahead and figure out which one's limiting. And we identify that our calcium nitrate is our limiting reactant, and we would end up producing 0.472 grams of calcium phosphate solid. Okay. Now our next part that we want to do is we want to identify what concentration of these ions are we going to get. So now what we want to figure out is the concentration of our sodium ions, what that's equal to, the concentration of our calcium ions, what that's equal to, the concentration of our nitrate ions, and our phosphate ions. So now in each of these, what we'll notice is that one of them we can determine without doing any calculations. So let's go back to our reaction up here, and we identified that our calcium nitrates are limiting reactant. So if we go back to our reaction, we could see that all of that calcium nitrate is all reacted away. There's nothing left. And so we say, well, where are all of our calcium ions? Well, now all of our calcium ions here are in the solid. Okay, so that means there are no calcium ions in solution. They've all been pulled into this solid. Well, since there's no calcium ions in solution, if we go back to our molarity definition, it's going to be moles of calcium that are a solute per liters of solution. Right now, they're all in the solid. They're no longer dissolved in solution. They're no longer a solute. And so we can go ahead and say, well, the concentration of our calcium ions would be 0. They're all fully reacted. It's part of our limiting reactant. Our limiting reactant's all gone. And so therefore we have no calcium ions left in solution. So let's go ahead and go back up to our sodium ions. Well, our sodium ions are going to be the moles of sodium ions that are a solute divided by the total volume of our solution. Well, if we go back to what we've already identified, we see here that we already know the moles of our sodium phosphate. Now, whether we have our sodium ions in our sodium phosphate or our sodium ions in our sodium nitrate, they will both be soluble. So here, if we want to identify the moles of our sodium ions, none of those are in a solid. So that means whatever we started with our sodium ions, we still have all those sodium ions still in solution. So if we want to determine the moles of our sodium ions, we can see we could use the fact that we know the moles of our sodium phosphate to get to the moles of sodium ions. Okay, so here we can see is that the moles of our sodium ions is going to be equal to our 0.00369 moles of sodium phosphate, and the mole ratio would be 3 moles sodium ion for every mole of sodium phosphate. We're just using our mole ratio that we have 3 moles of sodium ions for every mole of sodium phosphate. And so we would find that we would have, for our sodium ions, we would have 0.0111 moles of our sodium ions. Well, now we have the moles of sodium ions. Those are all still free in solution. None of them got pulled into the solid. So the concentration of our sodium ions is going to be 0.0111 moles of sodium divided by our total volume. So that would just be our 0.0204 plus our 0.0319 liters. And so that would end up being 0.0523 liters of solution total. And we would end up getting a concentration of 0.212 molarity of our sodium ions. Now again, here none of the sodium ions got pulled into solution. All of them are still dissolved, dissociated in our solution. Okay. So now if we go back to where now we want to identify the concentration of our nitrate ions. So again, we go back up to our reaction. Now we don't have any calcium nitrate left, but all of our nitrate ions are part of our other possible product, which would be our sodium nitrate. Well, that is soluble, so that means that whatever amount of nitrate ions we started with, that's how much we're going to have in solution still. So we go back up and look at, we want to calculate our sodium concentration, our nitrate concentration. So that's going to be moles of our nitrate ions as a solute divided by our total volume in solution. Well, if we want to go and determine the moles of just our nitrate ion, we could use our mole ratio, just like we did with our sodium ions. We see that we would have 2 moles of nitrate for every 1 mole of our calcium nitrate, and we could go ahead and we would calculate that that would mean we would have 0.00912 moles of nitrate. Okay, and we see that's just simply double the number of moles of calcium nitrate that we would have because of that mole ratio, and we still have the same total volume, 0.0523 liters. Again, just adding up our 2 individual solutions, and we would end up getting a concentration of 0.174 molarity. Okay, so now those 3 are more simple in identifying the concentration, right? The first one, our calcium ions concentration of 0 because it's all sucked in the solid. Sodium and nitrate, they both start with a specific amount. All of those ions are still in solution. Now if we go to our phosphate ions and we're trying to identify our phosphate ions, what we're going to notice is that this is going to be a little bit different. Okay, now the reason why it's going to be a little bit different is that up here, our phosphate ions are pulled into the solid, but not all of them are, because now we still have some excess phosphate ions, part of our excess reactant, the sodium phosphate. So in order for us to figure out the moles of our phosphate ions still as a solute, well, that's going to be the moles of excess phosphate. So the amount that we have extra that was left over after the reaction with our limiting reactant, the calcium nitrate. So there's 2 ways for us to do that. One of them is to find out the moles of phosphate reacted, and we can do that by finding out the moles of phosphate in the mass of calcium phosphate that we formed in our 0.472 grams of calcium phosphate, because that tells us how much phosphate was reacted. Okay, so we could do that as simply a mole to mass to mole conversion. So we would have 0.472 grams of calcium phosphate, and we could use our mole ratio. So our molar mass is 310.2 grams of calcium phosphate for every mole of calcium phosphate. And then our mole ratio in this compound is that we would have 1 mole of calcium phosphate. In that 1 mole, we would have 2 moles of our phosphate ions. And so then that would give us a moles of our calcium, of our phosphate that has reacted 0.00304 moles of phosphate. Now the other way that we can determine the moles of phosphate that is reacted is we could go ahead and we could look at our limiting reactant, right? Our limiting reactant is this 0.00456 grams of, moles of calcium nitrate. And from that, we could say, well, how many moles of phosphate would be needed to react all that, right? And that would be using our mole ratio. And we'd see it end up being the same number. So now we would have the amount of phosphate, real important here, that is reacted, okay? So if we're going to look at the amount of phosphate that is in excess, well, that's going to be about equal to the initial moles of our phosphate ion. And from that, we're going to subtract the moles of our phosphate ion that is reacted, which we just identified up here. Okay. Well, for us to figure out the moles of our phosphate that we started with, if we go back up here, we see that we have 0.00369 moles of sodium phosphate. Well, we have 1 mole of phosphate for every mole of sodium phosphate, so that would mean that that would be equal to the amount of phosphate that we started with. Okay, so now we have the initial amount, 0.00369 moles of phosphate that we started with, and we found that we reacted away 0.00304 moles of phosphate to form our calcium phosphate, and the difference is going to be 6.5 times 10 to the negative fourth moles of phosphate, and that is our excess amount that is still free in solution. Okay, so then we can go back up here and determine the moles of phosphate that we just found, 6.5 times 10 to the negative fourth moles of excess phosphate still free in solution, divided by our total volume, 0.0523 liters. Again, that's the sum of our two solutions we mixed. And we are going to get a concentration of 0.0124 molarity of phosphate ions still in solution. So now if we go back to kind of how we thought through this, to identify the amount of phosphate, so that's our ion that's part of our precipitate, but we had excess of it, we had to figure out how much of it was actually reacted away, how much did we actually start with, and the difference between that would be how much we have in excess, how much is still free in solution, and then we could go ahead and determine the concentration by dividing that by the total volume that we'd have. So hopefully this gives us a good way to think through this problem. Again, conceptually understanding this idea of a precipitation reaction, and that in our precipitation reaction we're forming a solid, but if we have an excess reactant, we still have the ions that would be part of that solid, like this, our phosphate, some of them still free in solution, whereas our calcium ions, since they're part of our limiting reactant here, would be completely pulled into our solution, giving a 0 concentration.